This is a really exciting episode of Funding Awesome. Most people think of NVIDIA as a hardware company that builds chips for training massive AI models, but I'm going to give you an inside look at a very different side of the story. I'm joined by Dion Harris, the Director of Accelerated Computing Go-to-Market at NVIDIA. Dion has been with NVIDIA for over 8 years, deploying the hardware and software infrastructure behind some of the most powerful AI models on the planet, not just for training, but for inference. And he had a few surprising things to say about DeepSeek and where generative AI is headed next. But generative AI is just one of the many technologies that I'll be covering live from GTC in a little over a week. GTC is NVIDIA's huge developer conference where they showcase the latest AI breakthroughs in every major market, from agentic AI and video games to robots and self-driving cars, the same science behind the stocks that I cover on this channel. And anyone who registers for at least one online session at GTC using my link below can win an NVIDIA RTX 4080 Super Graphics card. Simply attend a free session online, take a screenshot, and send it to me after the conference by going to tickersymbolu.com/GTC or by using my link below. GTC should be on every investor's radar, and so should NVIDIA's ecosystem for inference. Your time is valuable, so let's get right into it. Dion, it's so great to see you again after last year's GTC. For the portion of my audience who didn't watch our interview last year, why don't you tell us a little bit about what you do at NVIDIA and what you're going to be doing at GTC this year?
So my name is Dion Harris. I'm the director of our data center solutions group. And so what I spend most of my time doing is working with our customers and partners to really, understand how and where they're leveraging our platform and deriving the most value. So this year at GTC, we're going to be having lots of great sessions and discussions around just that, from everything from digital twins to AI training to, of course, AI inference.
And how long have you been at NVIDIA?
So I've been at NVIDIA roughly about 8 years now. And in that time, the company has changed, the world around us has changed. And so it's really interesting when I reflect back on my time at NVIDIA. When I first started, we were pretty much known as a gaming company.
Yeah.
And as AI started to evolve and the data center really became such a focus for not just NVIDIA, but the entire globe, it really has been exciting to see that shift take place, not just personally, but throughout the industry.
Actually, let me double click on that for a second. So when I think of NVIDIA, I usually think of AI training, but inference has been such a huge topic, especially after everything going on with DeepSeek. What do you think is NVIDIA's core strengths when it comes to inference?
So, when you think about NVIDIA, like you mentioned, we've definitely been leading the charge in terms of creating cutting edge training platforms to build large pre-trained foundational models. And so, when we talk about the chatgpt moment, that was largely born by the NVIDIA platform and obviously, and folks like OpenAI and others. But as we move into deploying AI, that's really where inference becomes, critically important. And when we talked last year, Alex, we highlighted Blackwell. And, what we really saw then, and I think what we're seeing now, is Blackwell was purpose-built for large-scale inference. And so a lot of the numbers that we talked about, if you go back and look at that video, we had lots of speeds and feeds going back and forth. But at the end of the day, that is really what translates into the 25x higher energy efficiency and improvement specifically for inference. And so Blackwell as a platform is truly going to revolutionize what we can do in terms of inferencing at large scale.
And so when I think about inference, I think of that as sort of the third step for AI, right? So the first thing we have is pre-training. The second step is sort of post-training. And there are many steps bundled in each of those. And then third is test time scaling. Can you sort of help us understand the differences and the strengths of the Blackwell ecosystem in each of those three areas?
So like you mentioned, the first step toward building an AI use case is building a pre-trained model. And like we said at the onset, NVIDIA has been developing lots of incredible technologies, whether it was our core cuDNN library that allowed frameworks to tap into the power of GPUs, looking at all of our innovations around NVLink, our innovations around InfiniBand and connecting large-scale infrastructures to really make sure that those training runs could happen as efficiently as possible. Again, you've heard of the scaling law, which is basically the more compute you have, the more intelligence is derived in that pre-trained model. But that's really just the beginning. Foundational models are useful But as you start to deploy them in your companies, in your specific scientific domain, you require additional intelligence injected into the model. And that's where you get into things like post-training and then test time scaling.
Okay, so post training is really more about the fine tuning of the model, then, not really building up the foundational knowledge, but more like I have a specialized set of knowledge that I want to really optimize this LLM for. And then inference is the actual prompting of the model and receiving a response.
You nailed it. And so when you think about post-training, like you said, because you're trying to fine-tune the model, there's a number of different techniques that are used, whether it's reinforcement learning, supervised fine-tuning, and now with reasoning, you actually have a whole new class of techniques that are being leveraged during post-training to inject reasoning and test time thinking into the model itself. And so what's really interesting and exciting is you see this confluence of the three phases. They're no longer separate and distinct. The way that you train and pre-train a model is now being influenced by whether or not you're trying to insert the reasoning capabilities. And then the way you do post-training now involves tons of inference and other capabilities to help the model learn how to think.
So it's really more of like a cycle or a feedback loop between the three phases, right? What happens in inference can even inform the next round of training, foundational training for the model. Is that right?
Absolutely. You have a handful of pre-trained models and lots of the names we know and love, OpenAI, Claude, Gemini, et cetera. And then when you look at the derivatives of those models, of course, some of the open source models like Llama and of course DeepSeek V3, like you mentioned, the post-training is really where you start to see the proliferation of derivatives of those pre-trained models, and everyone's taking those models and trying to make them their own, make them intelligent. But again, none of that is useful without being able to deploy it and use it for inference, because that's where you extract the value.
How much does the foundational training matter versus the post-training versus the test time scaling in terms of making an AI model feel more capable, more powerful, and more generally useful as it's deployed?
Really, it's a hybrid approach. And the reason why that is, when you think about it, it's kind of like the way we learn, right? First, when you start learning math, you have to show all your work, you need to think about it, and really make sure you're deriving the right answer. But eventually, you get to the point where you just know it, right? And so what we're starting to see is as you look at the pre-trained process, which is helping the model know and understand the world, you're seeing these sort of important feedback loops where now injecting reasoning back into the pre-trained model is creating this capability of the model to know it and learn it without having to think and recompute it each time. And so this is an area where you're going to see continuous evolution because, much like ourselves, we're always learning new information, new processes, and way of approaching different problem solving. So this same principle will hold true for AI models as well.
That's super interesting. I've been thinking about pre-training, post-training, and test time scaling as sort of three isolated things, but now I'm excited to learn more at GTC about how these things come together, their overlaps, how they feed into each other. One question I have is, so when we think about DeepSeek and we think about inference and we think about OpenAI, we really are talking about large language models, right? Mm-hmm. But they're really just the tip of the iceberg. Can you tell me what some of these developments mean for image generation models, video models, and models of other kinds that aren't just, chatbots or LLMs?
Absolutely. So when we talked about Blackwell's platform, one of the things we talked about was sort of the new transformer engine, and that was introducing the capability of FP4 precision. And what's exciting about that, it not just applies to LLMs, because we're using, sort of the intelligence of the hardware, but more importantly, the intelligence of the software to understand when and where you can use those lower precisions is translating into breakthroughs across a number of different domains. So for example, in image generation, you mentioned, we've seen examples where you can accelerate text-to-image models like Flux and others to achieve a 3x speed up in throughput. And that's really important because when you understand that you're using the same hardware, the same sort of core platform, and leveraging these software capabilities, you can get 3x more. That translates into 3 times more revenue or reducing the cost. So these types of enhancements are happening in healthcare imaging. And of course, robotics and physical AI is another key area where we're seeing some really cool breakthroughs in applications of this technology.
So let me just try to wrap my head around that for a second. So let's take medical imaging as an example.
Hmm.
If I am scanning an image, I'm trying to detect a cancer in an X-ray or something. Give me a concrete example of where I might choose to lower my precision to increase my throughput.
Yeah, no, that's a great question. So to understand how, sort of models behave, there's different layers and different sort of processes within the AI process itself. And so within the layers, you actually define where and when you can use some of the lower precision. So it's not like you're using it grossly on certain types of problems versus others. It's really for the AI process. It has multiple iterations just to spit out a single answer. So it
Yeah.
starts to understand where are the sort of areas where I can use a sledgehammer and where are the areas where I need a chisel to really sort of refine my answer, right? And so
Got it.
given that understanding of the model, we basically introduce areas where we can use the lower precision. And, we talked about medical imaging. Some of the diffusion techniques are basically having incredible impacts, especially for things like MRI scans, where they've been shown to improve overall efficiency by about 50%. And so without affecting accuracy. So going back to your question
Wow.
around how and where you use that lower precision, the goal is to use it so that you get more performance and more efficiency without affecting the accuracy of the prediction itself. And I think that's really sort of the core intelligence in the transformer engines. And as we talk about that, it's not just about creating the math and the chip itself.
So, all right. I gotta, my mind's blown here. So I gotta think about this for a second. So pre-training, post-training, and inference are actually have a lot more overlap than I thought, right? Another area where I think there's going to be more overlap than most of us realize is between training and inference itself. So,
Yeah.
for example, Jensen has previously said that learning is really one continuous process.
Today, we kind of learn and then we apply it. We go train, inference. We learn and we apply it. In the future, we'll have continuous learning. The training process and the inference process, the training process and the deployment process, application process will just become one.
Right? It's not you learn stuff and then you apply it. We can think of learning and inference really as one process instead of two separate ones. Would you agree with that?
Absolutely. And I think this was actually very apparent in sort of how, the DeepSeek model evolved. It really started with a base model, which is their V3 model. And so that was a pre-trained model that they used to basically learn and understand the world. And as they started using and introducing these fine-tuning techniques, these reinforcement learning techniques, they're able to transform that into a reasoning model. And then, as I described earlier, there's also this sort of ongoing dynamic where as your model starts to become more intelligent and learn things through its reasoning process, it can actually embed that in the pre-trained model. So that way you just know that there are, three R's in strawberry. You don't have to go through and reason through each example, right? And so that's really, like I said, this continuous process. And it's much like ourselves, like I mentioned earlier, the way that we learn is we first reason, we think, we ponder, and we come to a conclusion. And then as you begin to use those facts more often, you register in your brain saying, okay, I just know this. I no longer need to, do 2 + 2 is equal to 4 and prove it. I just know that number, right? So it's the same thing that we're seeing with AI. And one thing that I'll just highlight is having a platform that is built for both training and inference is what really is going to be extremely important, especially as you move forward, given this continuous feedback loop and this continuous learning cycle. When we rolled out Blackwell, we intended developers to use the lower precisions. That's what sort of DeepSeek, one of their core innovations. They were able to use, FP8 in that case of the hyperarchitecture to drive more efficiency. That's exactly why we built it, is so that it can help, use a lower precision where possible, and that the developers can really adjust their algorithms to take advantage of that. So now as we look into Blackwell, we're hoping that even more developers take advantage of that to make, the models in terms of their training and the inference even more efficient. So I guess the point I'm trying to get at is when you think about what DeepSeek did, it really was leveraging the platform the way we intended. In fact, when we described Blackwell last year, we talked about mixture of expert models as being sort of a thing that was happening, and that was really going to be able to take advantage of this architecture by having that large NVLink domain. You can spread a number of experts across the infrastructure, and that gives you a lot more leverage, if you will, in terms of being able to have a large model, but also having very specific, or we call sparse, activations. So DeepSeek just illustrated, some of the possible, and we think this is going to get even more sort of efficient as Blackwell comes to the market. So that was kind of the meta point I was trying to get across, which is, we expect this type of innovation on our platform. In fact, that's why we build in these features and capabilities so the developers can take advantage of it.
Actually, let me double click on that for a second. So when I think of the Blackwell platform, and when most of us do, I think we think about the data center chips, the large data center infrastructure. But I know that Blackwell is also going into, for example, project digits, cars, a lot of different devices at the edge, right? Is it the same Blackwell chip, or is one better for training and one is better for inference? How do those different Blackwell chips relate to each other?
Yeah. So the one thing that we've been really excited about, and you will see this very sort of loud and proud at GTC, is Blackwell as an architecture is truly permeating through every sort of layer of our portfolio. Like you mentioned the project that was highlighted at CES, which is Project Digits. And again, that takes a Blackwell processor, pairs it with a CPU, and creates, an AI supercomputer at your desk. And we recognize the power of our platform is in our install base. We have millions of developers, and therefore we want to help enable them wherever they are, whether they're doing desktop development, whether they're using cloud, whether they're using gaming and commercial cards to do some initial research and fine tuning of various models. We're making sure that Blackwell as a platform is basically represented in all of our form factors so that our developers can be empowered, right? And this has always been sort of a core tenet of the NVIDIA ecosystem, is really making sure that CUDA runs everywhere, no matter what type of GPU you have. If NVIDIA supports it, it runs CUDA. And so the fact that you're able to take your software that you built on your Digits platform and deploy it in DGX Cloud, leveraging the FP4 capabilities we talked about earlier with the transformer engines, leveraging the decode engines, leveraging the key technologies that are part of the architecture itself, really enables you to become incredibly productive. But also it allows you to right size, to deploy the infrastructure you need today, but knowing that any development work that you do won't be wasted. It will be useful as you deploy on larger or other infrastructure.
That makes a lot of sense. When I think about a lot of the chips that I read about, some of them are marketed more towards training, some of them are marketed more towards inference, right? But it seems like what NVIDIA is doing with Blackwell is really taking this holistic approach to artificial intelligence as a whole. Pre and post training scaling, as well as the test time scaling. They're treating learning and inference as one giant loop instead of two completely separate processes. They're deploying the Blackwell ecosystem everywhere, not just in the cloud, but also in different points of the edge. Is there anything else you want to tell us about the Blackwell ecosystem that's like foundational like that we should really be thinking about?
Just to sort of drive it home, when you think about sort of what types of resources are required for each of those phases, what we've done some recent analysis is when you look at sort of post-training, for example, that there's actually 30x more compute used in post-training. Because even though you're doing, sort of smaller compute intensive activities, you're doing a lot more of them. So if you look at the Llama pre-trained open source model, for example, there are over 100,000 derivatives of that model. So everyone is taking that model and building their own model. So it creates a new set of workloads. We're seeing the same thing with test time thinking. It actually creates 100 times more tokens than the traditional inference. And so because it also has this feedback loop where now you're introducing inference into the post-training process, and you're introducing intelligence through back propagation to the pre-trained model, it really is going to expand the data sets that you use for even pre-training. So it has this sort of compounding effect where we see it creating not just intelligence, but much more demand for the compute that we're seeing in the broader ecosystem.
So back before DeepSeek, let's rewind the clock like maybe a year or so, a year and a half. Training was thought of as the big compute-hungry process in terms of AI.
Right.
And then post-training scaling comes along. There are all these new techniques that end up costing more and more compute over time. and as a result are refining the model post-training, making it more effective. And now what you're talking about is this third step in inference, thinking longer on harder problems, chain of thought reasoning, using a mixture of experts approach to solving a problem. All of those are actually driving the overall compute demands up.
For post-training, we've seen that post-training is about 30x more than pre-training.
Got it.
We've also seen that the test time thinking compute, in other words, deploying reasoning models at scale, is going to end up generating 100 times more compute than even pre-training.
Whoa.
And the reason why is the proliferation in all the usage, right? Because when you think about it, if you just take a hyperscaler like Meta, they have 2.1 billion active users, right? And if you start to think about how and where they're using and engaging with AI and engaging with, some of these different AI models, the demand is much further than any one platform can supply today. And that's largely because these types of inferences that are going to give you much more intelligent, richer answers are going to require a lot more compute. And so that's really where we're trying to drive as much efficiency as possible. So when we talked last year, I talked about reducing the energy per token by 25 times. And the reason why we're doing that, we're one of the few companies that says we're going to give you a platform that allows you to use less, every year, because we know the demand is still, incredibly high. And so, as we continue to drive more efficiency and reduce the cost per token and the energy per token, that's a good thing for the industry, because that will allow more applications to adopt AI, that will allow more users to adopt AI. And so that's really the crux of how we're trying to drive innovation through our platform. So this has really always been, sort of our objective through a lot of the innovation we introduce.
I'm pumped for it. I have two quick personal questions for you.
Sure.
Based on everything we've talked about today, is there a particular industry that you think will transform first or feel this impact the most over the next couple of years?
Oh, that's a great question, because this is going to be such a broad sweeping sort of impactful change. I think AI is transforming nearly every industry, but I think one that's near and dear to my heart is really transforming healthcare. It's an area where you have incredibly scarce resources in terms of expertise and personnel who can really, sort of address all the patients and healthcare issues that exist in the world. And so by leveraging these technologies and leveraging intelligent AI to really not just, create faster diagnoses, but actually unlock new cures, new treatments, it's really exciting to see how that might unfold. The other is sort of what we have alluded to. I think, maybe it's the little kid in me that loves to see robots and autonomous systems, but I think physical AI is going to have an incredible breakthrough as well, because when you think about how complex it is to interact with the physical world, it will require thinking. It will require understanding, sort of the spontaneity of the world around us. And so I think as you look at some of these new technologies and processes as they evolve, it's going to make physical AI a lot more effective, and I would say it's going to be really fun to see how that takes off as well.
Yeah, I didn't even think of that, but we talked a lot about all the different ways that inference can scale, right? Just thinking longer step by step, chain of thought reasoning, etc. But, I was thinking of it like large language models and agents. It is really cool to think about how that would affect robots, like you're saying, where now all of a sudden it moves smoother. It's doing a better job taking in sensor data, looking at its surroundings, and navigating and interacting with them, because it can leverage all these same techniques at inference time, but for its own application. Again, navigation, whatever it's trying to do as a robot in the physical world. So this extends like way beyond large language models, image models, making video clips on YouTube, which is what I use it all for.
Sure.
I'm starting to really understand the impact for other applications, including robots. I'm sure there's a good conversation about self-driving cars in there, medical, like you said. Yeah, I'm actually a lot more excited than I thought I would be, just because I was still thinking about chatbots. So I'm really happy I asked that.
Yeah, no, like I said, the amount of areas or industries or domains that this is touching is really incredible. Another key area that I've been doing a lot of work in and I'm really excited about is some of the work that's happening to leverage AI for for the climate tech ecosystem, whether it's, using it for disaster recovery, whether it's using it to predict, some of the impacts of the wildfires we've experienced here recently in California.
Sure.
It's really, great when you see these technologies being brought to bear to really solve not just critical problems, but critical issues that face us in our day-to-day lives. And so, like I said, picking one is hard, but like you said, they'll have lots of wide-ranging effects that I think will have transformational benefits.
I'm super excited to learn all about that and more at GTC. I can't thank you enough for your time, Dion. Is there anything else you want to tell the audience what we should go watch at GTC, one session that you think is extra exciting, whether it's yours or someone else's?
There's a number of incredible sessions. I think one that I will highlight a little bit because it's really drilling in on the software. Because like I mentioned, we talk a lot about hardware, but when you think about, how complex these models are and these frameworks are in deploying models at scale, it's very challenging. There's one called a distributed inferencing serving framework for reasoning LLM models. And that's session S73042. And that will include some really incredible announcements, but more specifically, it's going to help customers understand how they should be thinking about deploying these reasoning and AI models at scale. Because that's really where most customers are now. They've seen the excitement, they've done all the POCs, and they're really trying to deploy these as efficiently as possible. So that'd be one session I would point folks to just to kind of get their feet wet and understanding what's the latest and greatest software that we have to help customers deploy these models.
Awesome. And I'll make sure to check out that session myself and report back what I find.
Thanks, Alex. Great talking to you again.
A huge thank you to Dion Harris for taking the time to walk us through NVIDIA's Blackwell ecosystem, breaking down the 3 AI scaling laws, and explaining how training and inference work hand in hand to make AI models way more capable over time. Not just language models, but everything from image and video models to medicine, robotics, and beyond. There's a lot more to Blackwell than just data center chips, and a great way to learn all about the science behind NVIDIA stock is to register for GTC and jump into a few online sessions. They're completely free, and I'll leave all the links below for your convenience. I'll announce the winner of that RTX 4080 Super GPU a few days after the conference. That way everyone has some time to enter. And another big thank you to NVIDIA for inviting me to cover GTC live again this year. And of course, a big thank you to you for supporting the channel. Thanks for watching, and until next time, this is ticker symbol U. My name is Alex, reminding you that the best investment you can make is in you.